All right. Good afternoon. Okay, so I'd like today to continue talking about the minimum principle. So, um, uh, you know, in lecture number 4, we talked about the variational approach. And the variational approach, the main assumption or the critical assumption there is that the Hamiltonian, or specifically L, is differentiable with respect to U, okay? And well, that excludes many problems, especially related to fuel optimal problems, as you will see hopefully later on today. So, so that's a restrictive assumption that the Hamiltonian needs to be differentiable with respect to U. And there are other critiques of the variational approach. One of them is that it's just only a local minimum. There is no possibility that you get a global minimum out of variational approach. Why? Because the main approach or the approach is based on differentiating locally near the optimal point. So that is also another restriction. So there are many number of restrictions that limit the applicability of the variational approach. So it solves the problem that we solved, in lecture, and also you saw some problems that you will see some problems. So hopefully I'm going to post another homework about variational approach. So we can use it to solve some problems, but not many. So we need a more general method of how to come up with the optimal controller. Okay, so that's the idea, and that leads to the minimum principle, or the Pontryagin minimum principle. Okay, so so here is like a general formulation of what we call here special problem 1, which is the case when we have free time and fixed endpoint. So I gave here a motivational example about an emergency braking system, autonomous system. In this case here, we have a target set. We call that a target set or target state, which is the final state in this case, and T1 is free. We have constraints on the input, and this is something also that is lacking in the variational approach. We need to consider constraints on the input, okay, for physical reasons. So how can we solve this problem? Okay, so this problem is a time optimal, if you think about it, but also fuel optimal, okay, because we want to minimize U, the magnitude of U, and we want to minimize the time. Okay, so hopefully through the minimum principle, we can solve that problem. Okay, so what is the minimum principle? So the minimum principle shares similar, if not the same, necessary conditions as the variational approach. Okay, except the condition that we need to differentiate the Hamiltonian with respect to U. Okay, so we will use the same conditions as the variational approach, except, right, except the resorting to the gradient of H with respect to U. We are not going to do that, right? And that allows us to consider Hamiltonians that are not differentiable with respect to U. Okay, so that's the idea. So what are the necessary conditions that we know from the variational approach? So first of all, we have the constraint of the dynamics of the system, and we also have the co-state. So we need to come up with what we call a hyperstate, another hyperplane. Okay, in addition to the plane of the dynamics of the system given by x dot, we need to come up with another hyperplane. We call it the co-state plane, which is given by the negative of the gradient of H with respect to x. Okay, which is equal, if you substitute by the definition of the Hamiltonian, that is the negative of the gradient of L with respect to x minus the partial derivative of f with respect to x transpose times p. Okay, or everything here at the optimal point, so everything in terms of stars. Now, there is another thing that is different than the variational approach here, which is the boundary conditions. So if you look at we need two boundary conditions because we have two differential equations. Of course, these are not scalar differential equations. Each differential equation has dimension. So in fact, if x is n, okay, we call these equations Hamiltonian system. We have the original system. Here we have what is the Hamiltonian system? The Hamiltonian system is composed of the original state of the system, of the system of interest, right? Plus the co-states. So if x has a dimension n, then the Hamiltonian system will have a dimension of 2n. Okay? So keep that in mind. And we need, of course, 2n number of conditions or boundary conditions for these equations to be solved. Okay? Now, if you pay attention here, like in the variational approach, we have one boundary condition from the x, which is typically the initial state, which is, what we know, right? Or we assume we know. And because here we are given the final state, okay, so we don't need, and we are not going to use a boundary condition on the P. So the boundary conditions are, both of them, right, that are needed are coming from the x. So you have x at t0 and x at t1. So these two are known and given, and we are going to use them to solve for U star, okay? Remember, our goal always is to find U star, the optimal controller that will solve the problem. That is our goal, okay? Any question up to this point? So this slide here summarizes theorem 5.5 of the Athan and Falb textbook. If you read the theorem in the textbook, it has more statements there. So this is just a loose summary, right, of that theorem, okay? So what the theorem says is, if U star is an optimal, is optimal, then there must exist a co-state P star such that P star and X star satisfy the equations of the Hamiltonian system, this one and that one here, with these boundary conditions, okay? So the triple X star, U star, and P star, they solve this Hamiltonian system. Okay, so the minimum principle basically says that, okay, the approach is almost similar to the variational approach. There is only subtle difference there, okay? So the subtle difference here is that, first of all, this is the definition of the Hamiltonian, which is the same as before, right? So here, for each t that belongs to the range from t0 to t1, H, the Hamiltonian, attains a global minimum, right? So now we can talk about global. Why we are going to talk about why we can talk about global here? Because we're going to search for the optimal point. We're not going to differentiate. We're not going to solve it or find it using differentiation, okay? So H attains a global minimum as a function of U over omega, which is the set of constraints, okay? And what do we mean by global? We mean by global that the Hamiltonian at the optimal point is always less than or equal to the Hamiltonian at any U. So the Hamiltonian at U star is always less than or equal to the Hamiltonian at any U, okay? For all U belongs to the constraint set of constraints, okay? And this is going to be a static optimality problem. It's not going to be dynamic, meaning we are not going to solve it using differentiation. This is the key difference, okay? And there is also another condition which is related to a special, so this condition H is equal to 0 is related to special problem 1 when we have free time and fixed endpoint. So when we have fixed endpoint and free time, we have this condition that H, the optimal H, is equal to 0. There is a special, there's another problem where H is going to be constant, not 0 at the optimal point, right? But that's, we are going to consider that at a different point, different time, okay? But for now, for this problem, special problem, this is what we have here. Please stop me at any time if there is anything that is not clear. Okay, so so this is section, so there is a discussion in section 5.17 of the textbook about, so there is a proof in the textbook. You are more than welcome to read the proof. It's a little bit lengthy. We don't need to do it, but if you want to have extra information, you are more than welcome to read through the proof, okay? Right after the proof in the textbook, there is a discussion or comments about the minimum principle. I highly recommend that you read these discussion points. But basically, here's a summary of the first 2 or 3 comments is that satisfying this inequality and this equality, right, and satisfying this theorem acts as a necessary condition for optimality, for sure for local optimality. For sure for local optimality, okay, according to the theorem. For global optimality, you need to argue, there is more argument to be involved, okay? But for sure, we have a local optimality, okay? Now, all right, so as I mentioned, right, our minimum principle says that we can solve for U star without differentiation, okay? How can we do it? So to see how we can do it, let's do something just quickly here. Let's add to the Hamiltonian, let's add, let's add to the cost. Let's add this identity, which is equal to 0, the integration from T naught to T1, P transpose F minus X dot, right? F minus X dot is equal to 0. So as if we are adding 0 here to the cost. So it's just a trick here, okay? So if you add this to the cost function, this is what you have. Now, if you replace P by P tilde, right? So you have minus P tilde, so you have minus P tilde here, transpose, and minus P tilde here, minus, you have a plus here, right? And now let's tweak the definition of the, let's multiply the Hamiltonian by a negative, okay? So if you do that, then this is the new cost function that we have, okay? So now looking at this cost function, right, then maximizing this term will minimize that cost function. That's number 1. And another thing that is, you will see now, I think it's best to show it, to show how we solve this problem. We want to minimize, we want U that minimizes this problem, which is related to this term here. Okay, so let's now consider time optimal control of a frictionless mass. Yes, go ahead.
Folder is not in the campus. Right?
What's that?
The folder.
No. Sorry. This is like I updated the notes that I used last time, so I'm going to upload this right after the lecture. So it's an updated version of the notes that. Yeah, thank you. So these notes are an updated version of the one that I used last time, and I'm going to upload this right after the lecture. Okay. So I fixed some of the typos here, and I added some notation. Reference to the sections in the textbook. Okay. So in
I
the
have a
textbook,
question.
chapter 7 is about time optimal control. And chapter 8 is about fuel optimal control, right? So, so fuel is just, means control effort, right? And time means time. So here we want to arrive at the optimal solution in the shortest time. That's what we want, okay? And so now we are in chapter 7. We jumped to chapter 7. So we skipped chapter 6 and we jumped into chapter 7, okay, of the textbook, which is about time optimal control, okay? Okay, so we are going to consider, the book calls it double integrator, okay? It's nothing but a frictionless mass. So it's basically you have a mass, that mass has a position, has a velocity, and it moves in a space, right, without friction, okay? And we want to solve, in this case, moving this mass in the minimum time, basically. That's what we want, right? So, so we consider here, in this case, one dimension, which is horizontal motion. So we have position, we have velocity, we have acceleration, which is the control input. So the acceleration here is the control input. So if we define x1 as the position and x2 as the velocity and u as the acceleration, then the equation of motion for the system is x1 dot is equals to x2, or the derivative of position is equal to velocity, and the derivative of velocity is equal to acceleration. And we are using the acceleration as the input to the system. So this is typically, this is the, I think I mentioned this last time, this is the simplest model for a moving robotic system, moving mass, moving vehicle, call it whatever you want. Any moving mass, right? In space, the simplest mathematical equations that you can use to define that mass, that movement of the mass, is x1 dot is equal to x2, and x2 dot is equal to u, okay? Of course, it's not a perfect model, but, you know, it can serve its purpose, okay? Depending on the application. All right, so this is the system, and the problem is we want to move this system from point x at t is equal to 0, which is equal to 0 in this case, t0 is equal to 0, from an initial point to a final point in minimum time. So t1 is free while satisfying, okay, u belonging to constraints, minus a max up to a max. Or we can write it in a set or in a range from minus a max up to a max, including, okay? So that is the problem. What makes this problem an optimal control problem is what?
Time.
Time, and also the constraint. So even there is even if the problem doesn't say minimum time, the fact that we have constraints, that makes it an optimal control problem. In control, you cannot solve this problem except by optimal control when you have constraints. If you don't have constraints, there is, I think, possibility that you can solve it without optimal control, like minimum principle and all that. But actually the defining feature of this problem is the constraints, believe it or not. Okay, so the constraints is important here to consider. Okay, and of course minimum time. So of course that also adds to the optimality here. So optimal time, a minimum time, and constraints are two distinctive features of this problem. Without these two, you can easily. I teach in another class, and I show them. Through controllability, you can come up with, by studying the controllability of the system, you can come up with a controller that moves from this point to another point, no problem, right? But what makes it optimal is, yes, minimum time and the constraints. Okay? So now, this problem we cannot solve it using variational approach. Why? Because of the constraints. Okay, so we're going to use now minimum principle to solve it. Okay? So, first of all, we need to define the cost function that if we solve it or if you minimize it, we would have solved the problem. Okay? So the cost function, because, you know, cost function here is only time, right? Which is, we mentioned this last time, which is, you can write it as from integration from 0 to t1 of 1 with respect to time. Notice in the cost function, there is no mention of the boundary, no mention of constraints, and no mention of the particular points we want to move the system from to. Okay, it's just that cost function. Okay? Something to think about. Okay, so we need other things to force the boundaries and to force or enforce the constraints, right? And that comes from the Hamiltonian system. This is the job of the Hamiltonian system, right? The Hamiltonian system ties everything together, right? Ties the minimum cost that we want to minimize, but also ties the initial and final points, and ties in also the constraints. This is why we need the Hamiltonian. Okay? So Hamiltonian definition is L plus P transpose F, right? F is the constraint of the dynamics of the system, so we need to pay respect, or we need to respect the dynamics of the system, and L is this cost here, and from the dynamics of the system, we can enforce, you will see, of course, these, you know, so from the dynamics of the system, it comes with it the boundary conditions. So we can tie in the boundary condition to the optimization problem through the F here. This is why F shows up or is needed as part of the Hamiltonian. So you can see that right away in this slide, right, once we arrive here at the Hamiltonian, you will see that we are considering the minimum time as in L here. So that will take care of that, right? We can see that we can take care of these 2 points through the boundary conditions of the dynamics, right? So, and P ties everything together. The only thing that is missing here is the constraints of the input. This is the only thing that is, we see now how we are going to satisfy that, right? How to satisfy this, okay? Okay, so let's see. So you will see, and this is what you will see today, you will see that we are not going to use differentiation to solve the problem, but that comes with the expense or at the expense of doing some extra work. So you will see later on that we need to do extra work to solve this problem relative to the variational approach, okay? All right, so so the co-state has the same definition as before. It's equal to the negative of the gradient of the Hamiltonian. Okay, so you take the Hamiltonian differentiated with respect to x1, it will give you. So if you differentiate the Hamiltonian with respect to x1, it doesn't depend on x1, so it's 0. And then you take the Hamiltonian differentiated with respect to x2, you will see it's equal to p1. Okay, so you have 0 and p1, you multiply it by negative there. Okay, so that immediately gives you 2 differential equations. Notice that the dimension of the system is 2, so n is equal to 2. Okay, so that immediately gives you p1 is equal to 0 and p2 is equal to minus p1 from here. Okay, add that to the dynamics of the system, x1 dot is equal to x2, x2 dot is equal to u. Add that to the boundary conditions, 4 boundary conditions for 4 differential equations. We end up with this here, the whole thing here. This is the Hamiltonian system, right? This is what we call the Hamiltonian system. Okay? We are now halfway there. We are now at the halfway there. We are not there yet. Why? Because I mean, if there are no constraints, then we can resort to variational approach and say, oh, okay, let's now differentiate this with respect to u, right? Differentiate this with respect to u, and that will give us P2, right? That's our optimal controller, and we are done. We are done, right? But now, no, we have this omega that we need to respect. We have this omega that we need to respect. So we cannot use the variational approach. So we are halfway there. We need to do more work now. Okay? So how can we minimize this Hamiltonian system while at the same time doing it over this omega set omega? That's the challenge here. Okay. The way we do it, we do it is basically by, it's a semi-manual optimization. Semi-manual optimization. What I mean by that is it's a static optimization. It's called static optimization. In this case, we look at the term that depends on you. In this case, the term that depends on you is linear. So you have P2 times U. Okay? So this is why you have to prepare. I have to prepare you guys. Okay, working with constraints is the hardest thing. Okay, so you have to go into this with patience. Okay, and willing to give to do some work. Okay, so with that in mind, you know, you look at the Hamiltonian, you see that it depends linearly on you. Okay, so that would lead to what's known as bang-bang control. Why? Because it appears linearly here, then H takes minimum values at minimum values of U, at the extreme points of U. At the extreme point, because it appears linearly. This is because U appears linearly here, okay? So what that means is, if P2, which is the coefficient of U here, right, is positive, well, that means for H to be minimum, right, take the minimum value of U, which is what? Remember, U takes values from minus A max to A max, okay? So obviously the minimum value of A max here is minus A max, right? So when P2 is positive, take the minimum value of U, which is minus A max. If P, on the other hand, P2 is negative, right, then take U star as A max. So obviously there is a switching that needs to happen here, and that switching happens at P2 is equal to 0. So at P2 is equal to 0, there's switching that needs to happen. Okay, so this is why it's called bang bang. You take the max or the min of U according to what P2 is. Okay, so you need to observe what P2 is, right? So which is what we would expect, right? In the variational approach, we know that the optimal controller is P2, linear, right? Like it depends on P2. So we know that U depends on P2, right? In this case, it depends, but in a different way. Okay, so we can now combine these two in this formula here, right? U star is equal to minus A max times the sine of P2, right? So if P2 is negative, the sign is minus 1. So take minus 1 times it. This would be plus A max. And if P2 is positive, then the sign of P2 is 1. So sine of P2 takes either 1 or minus 1. Okay? It's a function, either minus 1 or 1. In the book, there is no A max and B, it's just minus 1 and 1. So here is a more general, this is a more general treatment of the problem, okay? All right. So now what do we have? So we have x1 dot is equal to x2, x2 dot is equal, you substitute by U here, which is minus A max sine of P2 star, okay? We have the boundary conditions, and we have, because we have 4 boundary conditions, right? So hopefully we can solve this problem here. But let's move on. So if you integrate these two equations, if you integrate this one, right, so you end up with P1 is equal to some constant. If you integrate this one, you take this one, substitute it back here, so you have P2 dot is equal to minus C1, so integrate it, so you have P2 is equal to minus C1t plus C2, right? So these are the two equations for P. So now, so let me now switch to my handwriting. So I would like to go over some analysis here. Right, so let me now switch. Can you all see the notes? People in Zoom? Guys, can you see it, people in Zoom?
Yes, we can.
Okay, thank you. Okay, so now we're talking about the example. Okay, it's up to you whether you want to write with me or I'm going to upload this in Canvas. It's up to you. So we are considering time optimal control. What happened here? Time optimal control of a frictionless mass system. Okay, so let me write the Hamiltonian system. So the Hamiltonian system is given by x1 dot is equal to x2. x2 dot is equal to minus a max sine of P2. P1 dot is equal to 0. P2 dot is equal to minus P1. And we have the boundary conditions. X1 at 0 is equal to H naught. X2 at 0 is equal to V naught. So all these are given. And X1 at T1 is equal to H final. And X2 at T1 is equal to V final. Okay? So now integrating P equations leads to P1 of a time, P1 is equal to C1 because P1 dot is equal to 0. Okay? And notice here, and P2 of T is equal to, you take C1, substitute it back in the P2 dot equation, and then integrate, we'll end up with minus C1T plus C2. Okay? Now, it depends, of course, so P1 and P2 depends, they depend both on these constants, C1 and C2, obviously. And okay, so you'll see where I'm going with this one. So anyway, so if I sketch here P2 of t, okay? So you'll see that it depends on, it starts with C2 here, and it's a line, right? And that line has a negative slope, and so this is time, and this is P2 of t, and this is 0, right? So P2 crosses the 0, right? This is where the switching happens, right? And this point here, so when P2 is equal to 0, that point is C2 over C1. Okay, so that point gives you the switching time. So if you know C2 and C1, you know when to do the switching without even looking at anything, right? So if you know that. But you will see later on, we may use this or we may not. It's not very important to know C2 over C1. But that's that point, this point here of switching, right? And C2 over C1 is the time of switching, okay? So if you start at t is equal to 0, C2 over C1 is where you do the switching, right? And of course, obviously, this depend on the boundary conditions. Okay, so if I sketch now the control, the u, this is u of t, right? Then at the point of switching, what happens is when P, the control depends on P2, right? So when P2 is positive, right, the control will have a negative, will have a minus A max, right? And then when P2 is negative, right, the control will take A max. Okay? So this is how the control will look like. Okay? So let's continue with our, so what I'm doing here is just analysis, okay? So I want you just to follow on with me here. So x1 star of t and x2 star of t satisfy the equations x1 dot is equal to x2 and x2 dot is equal to plus or minus A max. Okay, because U is equal to A max is equal to minus A max times P2, so I can write it in a general form as plus or minus A max, and dx1. So if I take dx1, if I divide dx1 over dx2, right? So if I divide these two equations, dt will go with dt, and I will end up with x2 over plus or minus A max. You'll see why I'm doing this in a minute. And so that will lead to dx1 is equal to plus or minus 1 over A max x2 times dx2, which if you integrate both sides of this equation, you'll end up with a plane that relates x1 and x2. So then you have x1 is equal to plus or minus 1 over 2A max x2 squared plus C3, that constant. If you integrate both sides of this equation, Okay, this is the equation that you will get. Okay. Just give me a second. I'll come back to that. Okay. Okay, so this is for you guys if you want to continue taking notes. Okay, let me go next. Any question up to this point? So I can do the same now in the general sense, or generally. I can do the same, so I'm going to write it very quickly. Let's do that is equal to minus A max sine P2 star of t. If you divide both dx1 over dx2, so that would be equal to x2 over minus A max sine P2 star. Okay, so you have dx1 is equal to x2 over minus A max of sine P2 star dx2, integrate both sides. So that means x1 is equal to minus x2 squared over 2 A max sine P2 star plus C3. Okay. Okay. Why I'm writing this? Okay. I'm writing this because I can now visualize what happens. Okay. So this example actually is in section 7.2 in the textbook, okay? And in the textbook, if you want to see, if you want to plot these, you will see clear plots on this. But basically, if you write what we call the phase portrait, right, which is the plane that links x1 and x2, right? You will see that you know that this is not good. Okay, so, and then you have, okay, so the red ones are so the red ones here, this is the U is equal to minus A max. And the black ones here, this is the U is equal to A max. Okay, and basically, so this is, so if your x1 and x2, remember x1 and x2 are position and velocity. So starting any point, you start at this point, okay? So what happens is you okay? you apply the U is equal to Amax. So that's the control that so you'll be on that trajectory, okay? And I mean, these are just example trajectories, but these are infinite trajectories, okay? So we're talking about infinite trajectories here. Infinite possibilities, I should say, right? So these are like this, right? And the red ones are like this, going like this. Okay, so this is just what we call the phase portrait. Okay, so now,
Professor,
yes, go ahead.
now this trend, this is the optimal trajectory that
Yes.
we need.
Yeah, yes, that we will get
Other-
based on the optimal control. Yes. Okay, so now let me show you what we call the feedback synthesis or the controller, how the controller works. Okay, let me do it here. Okay, or let me do it maybe in the next. Okay, how are we doing this time? Time. Okay, so let's now look at what we call feedback synthesis. How the controller work. Okay. So this is X1 again and X2. So this is the phase portrait again. So we have the luxury that we have a two-dimensional system. This is why we can visualize this, right? If the system is more than two-dimensional, it's going to be very hard to see what's going on, okay? But because we have two-dimensional system, that's fine. So basically, so let's now take the case, this case here. Let's start here. So if you start here, so you have something like this. So this is U is equal to A max. U is equal to A max. Okay? You get here, you get to this point, then switching happens. When the switching happens, right, then you slide up to this one and you go to the zero. The point zero is the optimal point in this case here. Okay? Now, if you are here in this point here somewhere, right? So we have something like this. Again, here, so you have, you do the switching here, and then U is equal to, so on the black, you have U is equal to A max, going, so here, red and then black, and then here you have red, and then, which in this case, the red here will have A max also, and then in the black, you have U is equal to minus A max. Okay. Yeah, if you go back, I should have done it in the same way, right? So on the red, they have, this is, yeah, this is minus. Did I write? Yeah, this is minus. The black here is the minus, right? Which is unfortunately, it's the red here. It's this, it's the red there, U minus. Go there. So basically, in this case here, my cursor does not, oh, it works. Can you see my cursor here? Yeah. So basically, we're considering this, the red, and this black. And this red, and this black. You know what I mean? Yeah, this black. I'm not sure how to show this. This one, no. Anyway, so what we are considering, let me take the green. What we're considering is this one, this part, this part, this part, and that part. That's that. So I'm zooming now on a special case where I start here and I want to go to the 0, or I start somewhere here and I want to go to 0. Right? And so what is the controller that will do that? Right? So that's the controller that will do that. Right? And I need one switching, and there will be one switching. This is the case. If I'm here, it will take me only one switching, right? And then I will reach to the optimal point. If I'm here, it takes me only one switching. So at any point, you will need only one switching. Okay, so let me write it down. So oh, by the way, I forgot to mention here that this is known, so just for reference, I'm going to call this right half. And so right half this is a reference to the arc. So I'm going to introduce the terminology here, that is arc. So so this is a switching curve. We call this a switching curve. Okay, and this is the left half, right? And this one here is, this black here is the left arc, and this black here is the right arc. Okay, so U is equal to A max when X is on right arc. Right, so if I'm on the black, there's no need even for switching. Okay, so that's the right arc. Okay, U is equal to minus A max when X is on left arc. Okay. And U is equal to minus A max when X is on right half. So if I'm right half, which means that I'm in the red, right to the arc. Right half means right to the arc. Right? Arc is the boat that will take me to the optimal point, is the vehicle that will take, it's the road that will take me to the optimal point. Okay, so that's the black, either this black or that black. Right? So this black is the right arc, this one is the left arc. Right? Right half, I'm to the half of that arc, or left half means I'm to the left of that arc. That's what we mean here. And lastly here, this is equal to A max when X is on left half. I think I have, let's see. There you go. Yes, Alessandro. Yes, if you are not on the arc, then the controller will take you to the arc. Exactly. Right? Yeah, so if you are not on the arc, the controller will take you to the arc. That's nicely put, Alessandro. So there is, at max, there is only one switching, okay? And this is known as bang control. Okay. Any question?
The optimal point, we define it or calculate it?
What's that?
Now, this is all depend on the optimal point, which is the 0, 0.
Yes.
So is this like we defined before the problem, or
No, it's not. It's not. It's okay. So in this case here, so maybe I can write this. So this is related to uh, this u that will put you on an arc, right? Is this an optimal? Will lead you to the optimal point. The optimal point is not necessarily 0 and 0. It's the minimum that one can achieve. In this case, in this case, it's going to be the 0 and 0. Okay, but if you go back. So it depends on the problem. It depends on the problem. You cannot know it beforehand. That's
yeah? Why I ask this one? Because we said before the h equals 0
yes,
at the optimal point.
yes,
So just want to link this one with the
yeah. So I think in this case, because the final point is 0 and 0. Okay, so let me double check on that. Okay, because it depends on the final point. Okay, so there is a difference between the final point x1 and x2 and the final cost.
okay.
Okay, so probably in this problem here, because we don't have a final cost. So let me go back. Let me.
So here it's I mean
So this is why I'm hesitant to say yes or no to your question. I need to think about that. One second. So the cost function here is this one. Yeah, I need to double check that. Okay. Yes, that's right. So. Yeah, so the final cost is not going to be 0, right? But because the final cost is T1, and T1 obviously is not going to be equal to 0. It's going to be minimum something, right? But it's never going to be 0. So the final cost is not going to be equal to 0. Let's look at the Hamiltonian. So the Hamiltonian, if x1 and x2 is equal to 0, okay, does P1 and P, even if P1 and P2 are 0, there's no guarantee that the final, so I need to think about that. I need to think about that.
because we said in the condition.
Yeah, and H is equal to 0. Yeah, you're right. You're right. Let me continue this. Let me keep that in mind. Henry, you have a question?
Yeah, I have
I
a
was
question.
wondering,
One second, Joe.
wondering why the x2 is equal to 0 in the optimum, because we don't say that we have to be stopped, right? It's the question is just minimize, get to x2 or get to
So you
as as possible.
so you are saying in this case y0 here.
Yeah, wouldn't the solution be any point that intersects?
Yeah, this is related to his question, right? So his question is the 0 and 0 the optimal point that we would like to reach? In this case, apparently, yeah, my analysis is based on that assumption. I need to answer why is that? Yeah, I need to think about that. Okay, I don't have the answer right now. But both are related questions. Question from Zoom?
Yeah, I guess mine might be related, but it's based on when you switch. So, according to the switching logic you gave, it seems like we switch when we pass the y-axis. Is that correct? When
No,
it's
the
on.
switching, well, the switching is dependent on P. So the switching, so in this case here, I'm showing you what happens, okay? But switching, so basically what you do is, so the controller here is plus or minus, it's the, this one, this is the controller U, right? So this one here is U, okay? So U is minus a max sine of P2, right? So basically what you do is you solve these, you need all these equations, okay? And so the switching happens depending on the sign of when P2 is equal to 0. And so this can you repeat your question again, Jacob? I'm sorry.
Yeah, I guess just when do you switch? And I think you answered it. It's when P crosses
Zero.
the 0. And then
Yes.
P is defined by the C1T plus C2.
Exactly. Yes, that's
Okay.
the one. Yes, yes. Yeah. Okay, so at the risk of, I don't want to confuse you more, let me stop here, okay? And probably I'll try to give another example that will clarify things that are not, they may not be as accurate that I would like them to be, okay? But for now, switching happens according to P, and the switching also happens if you look at x1 and x2, according to this right half, left half, right arc, left arc. Okay? I'll get back to you regarding the optimal point. Okay? But yes, h has to be equal to 0. Okay? Now, 0 and 0 is related to h is equal to 0. This is something I need to double check. Okay? Yeah. Okay. So how are we doing with time? Still maybe have 10 minutes. Let me introduce next example, okay? Okay, so this is example in chapter 8. So this is fuel. Now we are going to talk about fuel optimal control of the same system. We are going to take the same system as a moving example here. Friction less mass point. Okay. So this stuff, you can find it in sections 8.4 up to 8.5 of Athens and FAR. There is also, if you are interested, there is a section 2.5 of gearing. Textbook, you find it in the syllabus. Right? Gearing also talks about this problem. So what is this problem? So this problem, the same system, so you have x1 dot is equal to x2, x2 dot is equal to u, and so we have the function is equal to x2 and u, and x at 0 is equal to h0 v0, and x at t1 is equal to hf vf, and t1 is 3, okay? U again belongs to a set omega, which is equal to minus A max and A max. And what we are interested in is to minimize the fuel. Okay? It would be nice if we can minimize the fuel in minimum time, but our primary concern here is the fuel or the control effort. By fuel, I mean electricity, energy, right? Anything that moves the system, right? So fuel is just, you know, it could mean a lot of things. So what is the cost function in this case? So the cost function in this case is from 0 to T1 magnitude of OT with respect to time. Okay, so that is the cost function. So we want the magnitude to be minimum as possible. Minimum. We need to minimize the magnitude of U, control effort. Okay, so this is in chapter 8. Chapter 8 is called optimal fuel problem. So we want to move the system from point A and to point B using as minimum energy as possible or minimum fuel as possible. All right, so let's solve this problem. So solution. The Hamiltonian is equal to L plus P transpose F. So that would be equal to the magnitude of U plus, so this is F, X2 on U. What happened? Looks like I don't have. Okay, still here. Let me just make sure. Unfortunately, I have some technical issues, so I need to take care of that. So I'm going to stop here. I don't want to overwhelm you even. So this may be a good point to stop. Please read chapter 8. So I'm going to solve this problem. The problem is you have the same system, the same constraints, but instead of minimizing time, I want to minimize U, magnitude of U, okay? So we're going to follow a similar approach to what, we're going to use the minimum principle, similar approach to solving the problem, okay? So we'll do that next week, next lecture. All right, thank you guys and see you next time. Let me know, people in Zoom, if you have any question. Thank you guys.